Next, we look at measures of variation. Now, measures of variation tell us how spread out a data set is. We'll be looking at a number of measures of variation, including the range, the variance, the standard deviation, the interquartile range, and the coefficient of variation. Now, the range is defined to be the length of the smallest interval that contains all of the data. So if we think about plotting the data in our data set on a number line, and then drawing the smallest interval that contains all of the data, the length of that interval is the range of the data set. In terms of how to calculate that, what we do is we take the largest value in the data set and subtract off the smallest value in the data set. If you think back to when we looked at first processing a data set, one of the first things we did was look at how to construct a data array. I was asking if you could tell me what the largest value and the smallest value in a data set were, looking at the raw data, and we saw how difficult that was, but it was very easy when we calculated that ascending data array. Well, one of the reasons we need the extreme values, the largest and smallest values in a data set, is if we want to calculate the range of the data set very easily. Now, one of the characteristics of the range is that obviously, as we can tell based on how we calculate it, it does not use all of the data in a data set. In fact, it only uses 2 values. And so if we had 10 values in a data set, we would only be using 2 values, or 20% of the data set, to calculate the value of the range. If we had 100 observations in the data set, then we would be using 2%. If we had 1,000 observations in the data set, then the range would only be using 0.2% of the data in the data set to calculate the range. And so you can see that as the size of the sample increases, the percentage of the data that are used to calculate the range decreases. Because the range is calculated using the most extreme values in the data set, in particular the largest and the smallest values, the range is highly sensitive to extreme values. On the other hand, for a given data set, there is one and only one value for the range. In other words, the range is unique. We could also say that the range exists, but also it's unique. Now, in order for the range to make sense as a measure of variation, the data need to be at least at the interval level. So either the interval level or the ratio level. And the reason that has to be the case is because we're taking the difference between the largest and smallest values. And you'll remember that data that is at the ordinal level or below, the ordinal or nominal level, differences don't make sense, right? Differences are defined and make sense only at the interval and ratio levels. And so in order for the range to be a meaningful measure of variation, the data have to be at least at the interval level. The fact that the range only uses 2 observations in any given data set causes it to be really sensitive to extreme values. And we may think, look, we want a measure of variation that uses all of the data in the data set, because there is information about the variability in a data set in all of the observations. And one measure of variation that uses all of the observations in the data set is called the variance. The variance is the average squared deviation about the mean of the data set. So to calculate the variance, you first have to calculate the mean of the data set, and then what you do is you have to calculate the difference between each observation and the mean, and then square those differences and average those squared differences up. Now, in doing this, we see that the variance is in fact using all of the data in the data set. But because it is using all of the data in the data set, and in particular it is using the most extreme values, and also because in calculating these squared deviations, the farther an observation is from the mean, the greater that squared value is. And so if you've got some observations that are fairly far away from the mean, then when you square those differences, that's going to inflate the value of the variance. And so the variance is sensitive to extreme values. In addition, the units for the variance are the square of the units of the data. And so, for example, if the data consist of lengths or distances, for example, maybe lengths measured in feet, then the units for the variance of that data would be feet squared or square feet. If the data represent income data, where the units are dollars, then the units of the variance of that data would be dollars squared or square dollars. And if we wanted to try to interpret the variance, then in some of these cases like I just described, I'm not quite sure how to interpret a square dollar. I know how to interpret a square foot, but I'm not quite sure how to interpret a square dollar. All right? So we'll keep that in mind as we move on to the next measure of variation, but we'll finish this out talking about the variance. For a given data set, the variance exists and it's unique. So for a given data set, there's one and only one value for the variance. Now, because in its calculation we are calculating deviations or differences between each observation and the mean, then in order for the variance to be meaningful as a measure of variation, the data have to be at least at the interval level or the ratio level. Now, the fact that the units of the variance are the square of the units of the data can make interpretation of the variance somewhat cumbersome or problematic. And so oftentimes we want to get back to a measure of variation that has the same units as the underlying data. And one way to do that is to just take the square root of the variance, because when we do that, remember, we have to take the square root of the units of the variance as well. And so if the units of the variance are the square of the units of the original data, then when we take the square root of those squared units, we get back to the units of the original data. And so the standard deviation, by definition, is just the square root of the variance. Because the variance uses all of the data in its calculation, so does the standard deviation. The variance, as we said, is sensitive to extreme values, and so the standard deviation is as well. But because we're taking the square root of those variance values, the standard deviation is really not quite as sensitive to those extreme values as the variance. As we said, which is the motivation for using the standard deviation, the units for the standard deviation are the same as the units of the data. Because the variance is unique for a given data set, so is the standard deviation. Let me just point out here that in order to get to this uniqueness claim, when we talk about the standard deviation being the square root of the variance, it's technically the positive square root of the variance. And then finally, in order for the standard deviation to make sense as a measure of variation, the data have to be at least at the interval level. So either interval level data or ratio level data. Now, the interquartile range is often used when we're using the quartiles as measures of location. So Q1, Q2, and Q3, Q1 being the 25th percentile, Q2 the median, and Q3 the 75th percentile. And so when we have the quartiles and are using them as a measure of location, perhaps, and so we would also have the median then. But typically the measure of variation that one would use in that situation is the interquartile range. And the interquartile range is the length of the interval that contains the middle 50% of the data, right? And the middle 50% of the data being represented by the first and third quartiles. And so the interval from Q1 to Q3 inclusive contains approximately the middle 50% of the data. And by definition, the IQR, the interquartile range, is the length of that interval. The way that we calculate this is that it's the difference between the third quartile and the first quartile, so Q3 minus Q1. Now, because the quartiles do not use all of the data in their calculation, neither does the interquartile range. And also because the quartiles are not unique, they're not necessarily unique for a given data set, neither would the interquartile range be necessarily unique. Now, because the quartiles are not very sensitive at all to extreme values, what that means is that the interquartile range as a measure of variation is not that sensitive to extreme values either. And so that's one of the advantages to using the interquartile range as a measure of variation. It's robust with respect to extreme values. The last measure of variation that we'll look at is the coefficient of variation. And so if we were talking about, for example, using the standard deviation as a measure of the variation in a data set, if I were to ask you, suppose we have a data set and the standard deviation is 1,000. And I were to ask you, is there a large amount of variation in that data set? Well, it really depends on the magnitude of the mean of the data set. And so, for example, if the data that we're talking about were the prices of computers, which range, let's say, from $800 up to about $2,500, and let's suppose that for the data set that we had a standard deviation of $1,000, then there's quite a bit of variation there relative to the magnitude of the variables that we're measuring, so the dollar amounts, all right? On the other hand, if we're talking about home prices, and so home prices, let's suppose that in the data set that we have, that the home prices are, averaging about $150,000. Well, in that case, if the standard deviation was only $1,000, I mean, you've got a very, very tight, or you've got a data set with very little variation, right? So a standard deviation of $1,000 would be minuscule, it'd be very, very small if the values in the data set averaged about $150,000. On the other hand, a standard deviation of $1,000 would be quite a bit if the values in the data set averaged about $1,000. So one way to kind of take the magnitude of the mean into account is to divide the standard deviation by the mean, and then we would also typically multiply that by 100%. Now, when we do this, we get a unitless measure of variation. Now, it's unitless because if we think about this, the mean of a data set has units that are the same as the data in the data set. And we also found out, or we discussed briefly, that the standard deviation of a data set also has units that are the same of the data in the data set. And so if you divide the standard deviation by the mean, you have to make sure that you are dividing the units as well, and since they have the same units, they would cancel out. So we get a measure of variation that is unitless. The coefficient of variation is useful for comparing the variability of data that have different units of measurement. And this is often used, for example, the lab sciences, say chemistry or biology, sometimes in the agricultural sciences as well. But I've heard it used mostly in the lab sciences. And you often want to get an idea of how accurately measurements have been taken. And one rule of thumb is that if your coefficient of variation is more than, say, 10%, then you really have a lot of variation in your data set, and so you may want to try to refine your technique in order to try to decrease the relative variation in the data set. Now, because both the mean and the standard deviation are unique for a given data set, the coefficient of variation, or the CV, is unique as well. And because both the mean and the standard deviation require data at least the interval level, then the coefficient of variation, in order for that to be meaningful, the data have to be at the interval level or higher as well. So those are the measures of variation that we'll look at. We will continue to look at some of these as we get into some more detailed notes on how to do the calculations and so forth. But again, we just wanted to give some definitions of these quantities and to discuss some of the characteristics and some of the requirements in terms of the level of data that we have to have in order for these measures to be meaningful.